We've looked a lot at circular motion concepts. We're now going to start looking at actual problem solving with circular motion. And the biggest thing that I can tell you about these problems is they're really no different than the F equals ma problems. We're still dealing with forces. Forces cause that object to accelerate inward for that centripetal acceleration, so we're still going to be dealing with that. The only thing that's different is we have a new way of finding our acceleration, okay, that v squared over r equation. And the other one is sometimes it just, we have to think about those concepts we talked about earlier about that inward acceleration. And a lot of times we have to think about what is actually causing that inward acceleration. So for this problem here, we have a 1,200 kilogram roller coaster traveling at a constant speed of 14 meters per second around a loop with a radius of 15 meters. Not completely accurate, it probably would be speeding up some, but we're just going to go with it. We want to know how much force does the track push down with at the top of the loop and how much force does the track push up with at the bottom of the loop. So we're going to start like any force problem by drawing free body diagrams. So when we're at the top of the loop here, we're going to have the force of gravity acting on the object, of course, and we're also going to have the force of the track. We can think of that as a normal force or just think of it as Ft. It really doesn't matter what you call it. Because the center of our circle is down here and we're accelerating inward, our acceleration is also going to be down. So I'm going to go ahead and set up some of the forces. In this case, it's going to be in the y direction. And so the forces we're going to have, I'm going to do Ft plus Fg equals ma. Now you certainly could change the signs of those. What I did is I just said down was the positive direction, and so both forces going down are positive and our acceleration going down is also positive. If you wanted to make them all negative, that would be valid as well. So we're going to substitute in a few things here. We know that Fg is just mg, and we know that our acceleration when traveling in a circle is v squared over r. So I can go ahead and substitute in for some of the things that I know here. I know my mass is 1,200 times 9.8, and that's going to be equal to 1,200 times my velocity squared, so 14 squared all over 15. So then I end up getting that Ft plus 11,760 equals 15,680, and so my force of the track at the top is going to be 3,920 newtons. Okay, transitioning to the bottom, I'm going to set up my free body diagram once again, and that's going to end up changing my F equals ma sum. The forces acting on the object when we're at the bottom, we have the force of gravity going down still. The force of the track now is going up because the track is underneath it, or you can call it a normal force once again. And our acceleration towards the center of the circle is also going to be going up. So our F equals ma, this is for question B here, is going to change slightly. So it's going to now be Ft minus Fg equals m times a. We're going to substitute in the things we know. So Fg is going to be our mass, 1,200 times 9.8, just like it was before. And then that's going to be equal to 1,200 times our acceleration, which is still 14 squared over 15. All right. And so when we go ahead and solve for this now, it's going to be Ft minus 11,760 equals 15,680. So that means that our new force of the track is 27,440 newtons. So obviously a little bit bigger, which makes sense because when we're at the bottom of the track has to overcome the force of gravity and still provide that inward acceleration. Whereas when we're at the top, the force of gravity and the track go in the same direction. They help each other out. We're now going to look at this situation where the roller coaster is about to fall off the track, and we're going to solve for the minimum speed that the roller coaster needs in order to not fall off the track at the top of the loop. Okay, obviously if it's just stationary, upside down, it's going to fall off the track. So we're going to see how fast does it need to be going in order to not fall off the track. So, force-wise, the forces we have acting on this object on the roller coaster at the top of the track, we obviously still have gravity. Here's the really, really important concept here. Before, we had put a force of the track going down, but we're thinking about the situation where it's the smallest possible speed without falling off of the track, meaning we're at the point where if we were going any slower, this object's actually going to fall off of the track and lose contact with the track. If that is true, okay, if we're at that point, that means there is no force from the track, okay? This roller coaster is at the point where if it was going any slower, it would actually lose contact. And if it loses contact with the track can't be exerting a force on it. So we're thinking about that situation where it's going around this track as slow as possible so that it just barely stays in contact with the track, but the track doesn't actually provide any force. We know our object is accelerating inwards because it's traveling in a circle, and so when we go and set up our F equals ma, it's just the force of gravity that's providing that inward acceleration. And so it's just going to be Fg equals ma, so mg equals m times v squared over r. We could put in the mass because we know that mass from the previous problem was 1200, but it just cancels out, so I'm not even going to bother. I'll substitute in for g, which is 9.8, and for our radius, so if we go back to the previous slide, our radius was 15 meters, okay? So I can plug that in, multiply both sides by 15, and I get 147 equals v squared. So my velocity is 12.1 meters per second squared. That is the slowest that roller coaster can be traveling without falling off the track when it gets to the top. For this next problem, we have a situation where a car is going around a circular track. All right, and we know the coefficient of static friction between the car and the road is mu. And the first question is, if friction is the only force keeping it in a curve, what is the maximum speed the car can have without skidding? So there's a little trick with this one when we go to set up our free body diagram, and that's the first thing we should do because we always are setting up our free body diagram first. And the trick is we're thinking about what I call the side view, okay? And here's the reason why we're doing this. If you're thinking about this, you have, acting on the car, we have a normal force and gravity going vertically. We're accelerating to either the right or the left because the car is turning, and the car is traveling forward. So that ends up being three different dimensions, okay? The vertical, up and down for normal and gravity, left and right for the turn, and front and back for the velocity. And that gets a little bit confusing, okay? And that's difficult to draw on a two-dimensional paper. So what I do when I draw my free body diagram is I imagine the car is coming out of the screen or out of the paper towards me. All right, so if we were looking at the car, its headlights would be on the front here. You would have the people sitting in the car, and I know this is a terrible drawing, but the people sitting in the car like that, and the car is actually driving towards us. All right. So that's the view I'm going to be thinking about when I go and set up my free body diagram. And I'm going to be assuming it's traveling in a circle that kind of looks something like that. Okay, turning to the right. If you were a driver in the car, you'd be turning to the right. So from that perspective, let's think about the forces we have. We have the normal force going up on the car from the road. We have the force of gravity going down. We know that we're accelerating towards the center of our circle here. And so there must be some force causing us to accelerate. This is another weird thing conceptually, okay? But the force that we have that makes this go towards the center is friction, okay? We have an inwards frictional force causing our car to turn. And the thing I always think about, and now I'm switching to the overhead view here, but the thing I always think about is if you have a car driving down the road, all right, and it enters a turn, all right, and the car tries to turn, but it's a wet, slippery surface, all right, or an icy surface maybe, and there's not really much friction, what's going to happen? The car is going to be going straight. It'll try to turn, but it ultimately will just skid right through the turn. We need that frictional force pushing it inwards, okay, and allowing it to turn. It's also a static frictional force, and the reason for that is that when you're turning, ideally you're not skidding, okay? Even though you're moving, your tires are rolling, they're not actually skidding or sliding along the surface of the road. So we are dealing with static friction in this case, not kinetic. Now that we have our free body diagram set up, I'm going to go ahead and write my F equals ma equations. So in the x direction, we have the force of friction, that's what's keeping it moving in a circle, equals m times my acceleration, which I know is v squared over r, since we're traveling in a circle. In the y, I'm going to have Fn minus Fg equals 0, because we're not accelerating vertically as we go in this circle. So that means that my normal force in this case just equals mg. I'm going to substitute in for the force of friction. I'm going to say it's mu s times my normal force. I can say that the force of friction is equal to mu times my normal force. Even though I'm dealing with static, I'm worried about the maximum speed. So that means friction will be at a maximum. And that's going to be equal to m times v squared over r. Substituting in for my normal force and plugging in this coefficient of friction, I have mu mg equals m times v squared over r. The m's divide out, and I get mu gr equals v squared. So that maximum speed ends up being the square root of mu gr. And there's my answer to part A. Moving on to part B, we want to know what is the car's period of revolution in terms of the given variables. For that, I'm going to start with v equals 2 pi r over t. That's our setup for the velocity of an object moving in a circle. And I'm going to substitute in that velocity that I just found, mu gr, square root of mu gr. That's going to be equal to 2 pi r over t. I can go ahead and cross multiply here, and I get t times the square root of mu gr equals 2 pi r. So that means that my period of revolution, and this is a little bit messy here, but it's going to be 2 pi r over the square root of mu gr. And there I have my answer to part B. For part C, we're asked how would the maximum speed change if the radius were doubled, assuming there's no other changes. So what I'm going to do for that is I'm going to take my equation for the maximum speed, v equals mu gr, okay, and I'm going to set up a new equation, all right? So my new equation is going to be v prime, my new maximum speed, equals the square root of mu g 2r, twice as much radius. And now I'm going to go ahead and solve for my new v in terms of my old v. There are a few ways of doing it, but we could square both sides to get rid of the square root because that's a little bit messy to deal with. What I'm going to do, though, is I'm going to actually factor out this 2 here. Okay, so I'm going to rewrite this equation as the square root of 2 times the square root of mu gr. Okay, and that's perfectly fine to write. Okay, we're simply multiplying those things together, and we can split them into 2 roots like we just did there. And when I do that, I see that this and this are the same, so I can just substitute that in, and I get that my new velocity would be root 2 times my original velocity v. Same situation for D, okay, we're looking for our new velocity v prime when our coefficient of friction is cut in half. So v prime is going to be the square root of mu over 2 times gr, okay. I'm going to do the same basic thing there and pull out that number, leaving root mu gr, so really we can rewrite this as the square root of 1/2 times the square root of mu gr. This expression here is our original velocity, and so that means that v prime is equal to the square root of 1/2 v Or we could say v prime is equal to v over the square root of 2. Okay, same difference because square root of 1/2 is really 1 over the square root of 2. And there we have our last one. Again, there's a lot of ways mathematically to do that. I think this way is the easiest though.